This video deals with momentum. Momentum is defined as the product of mass times velocity. Symbol for it you'll often see is P. No special units, just units of mass, kilograms times velocity, meters per second. Newton's second law was initially stated as force is equal to the rate of change of momentum. So this is the way Newton stated it. So the force is equal to the change in momentum divided by time. Well, if momentum is mv, then change in momentum is m delta v over delta t. And of course, delta v over delta t is acceleration. So we get F equals ma, what we're familiar with Newton's second law. So these two equations are equivalent. Now, another aspect of this equation is if you multiply both sides of this and this by delta t, you end up with F delta t equals m delta v. And this product of F delta t is defined as impulse, and the units are Newton seconds. And of course, m delta v is change in momentum. These two are numerically equal to each other. The impulse is numerically equal to the change in momentum, and the units, Newton seconds, are equal to kilogram meters per second. Okay, lots of applications to this. One of them has to do with airbags in cars, a very important topic to all of us that drive. And the purpose of the airbags is to maximize the amount of time that a force is applied. So let's give an example. You're in a car and you're driving along, and unfortunately you hit a tree and your momentum is abruptly brought to zero. So there's got to be a force on your body in order for this to happen. Now, if it's the steering wheel, then that's going to apply a force an extremely small amount of time. So this delta t is going to be very tiny, which means that this force has to be very large. On the other hand, if you're in an airbag and you sink in gradually, the time that you're in contact with the airbag is much larger, and therefore the force is a lot smaller. Now, lots of applications of this in sports too, where you want to actually maximize the momentum. So in that situation, you want to try to apply the force for the longest period of time possible. So that's why coaches say, for example, teaching you how to hit a ball with a bat, follow through is so important, because follow through will maximize the time that the bat and the ball are in contact with each other, and therefore maximize the impulse and thereby maximize the change in momentum. Okay, a quick example here. We want to find the change in velocity of a 1 kilogram baseball if 60 newtons acts upon it for a period of 0.1 seconds. So we're going to use this impulse momentum. We're going to solve for delta v. That equals F delta t divided by m. We plug in the appropriate numbers, and the change in velocity of the baseball is 6 meters per second. Here's a problem related to what we were talking about in the previous slide. We've got a 75 kilogram person riding in a car, 20 meters per second. The car runs into a bridge abutment. We want to calculate the force on the car if the person is stopped by a padded dash that compresses 1 centimeter, as opposed to the average force if he's stopped by an airbag, which compresses 15 centimeters. So we start with the impulse momentum equation, and we're going to solve for the force. That's what we want to find. But we don't have the time. The problem didn't give us the time. It did tell us that the dashboard was compressed 1 centimeters. So we can assume that the deceleration of the person was uniform, and so we can calculate the average velocity of the person by taking the initial velocity plus final velocity divided by 2. This is one of our previous kinematics equations. Now the final velocity is 0 because ultimately the person comes to rest, so therefore it's just the initial velocity divided by 2, so that gives us 10 meters per second. So now we can compute the time because we know that average velocity equals displacement divided by time, or time is equal to displacement divided by the average velocity. So the displacement was the compression of the dash, and the average velocity was 10 meters per second. So that gives us a time interval, very short time interval of 0.001 seconds. Now we can compute the force, and we end up with 1.5 times 10 to the 6 newtons, a very large force. That's about 1.5 million newtons. Okay, now compare that with the airbag. Now the time interval for the airbag is going to be the same formula as we used here, but now the delta x is 0.15 meters, 15 centimeters, divided by the same average velocity. So that gives us a time interval much larger of 0.015 seconds. We now compute the force, and the force is 1 times 10 to the 5th newtons. So you can see that this is considerably less than this force. One of the reasons momentum is so important is because it's a conserved quantity. So conservation of momentum states that assuming no outside forces on a system, the total momentum of the system remains constant. So typically these kinds of problems might involve collisions, for example. So if you've got two objects colliding, this would be the momentum of object 1 before the collision. This would be the momentum of object 2 before the collision. This would be the momentum of object 1 after the collision. And this would be the momentum of object 2 after the collision. Individual momentums might change, but the sum of the momentum before must equal the sum of the momentum after. Okay, so here's an example. We got a 1,000-kilogram train moving with a velocity of 8 meters per second, collides with an identical train at rest. We want the trains latched together. We want to find out their combined velocity. So momentum of train 1, its mass is 1,000 kilograms times 8 meters per second. Momentum of train 2, well, that's 0 because that train is at rest. And after they collide, the trains latch together, so essentially we just have one mass, and its mass is combined, the sum of the two individual trains. So that's 2,000 kilograms times the velocity of the combined train, which is what we want to solve for. So we solve for VC, and that comes out to be 4 meters per second. Okay, here's a slightly different kind of problem. We've got a rifle that shoots a bullet, 8 grams, with a velocity of 75 meters per second. We want to compute the recoil velocity of the rifle. Now this one's kind of interesting because before the gun is fired, the momentum of this rifle bullet system is 0. But after it's fired, we've got the bullet moving one way and the rifle recoiling in the other direction. So we can say that 0 is equal to the momentum of the rifle plus the momentum of the bullet. So therefore, if we're solving for the momentum of the rifle, we can say that m1v1 is equal to minus m2v2. Or, solving for v1, we get this. So this is the mass of the bullet times the velocity of the bullet divided by the mass of the rifle, and we solve for v1, and that's negative 0.12 meters per second. Okay, now we're going to talk about something that's called an elastic collision in one dimension. And an elastic collision is one in which kinetic energy is conserved in addition to momentum. So let me just say that all collisions, momentum is conserved, but only in some collisions is kinetic energy conserved. And actually, these are pretty rare because anytime two things collide, you usually hear a click or a bang or something that indicates that energy is being lost as a result of the collision. We do a lab on my face-to-face class where we have two cards with magnetic bumpers, and the two cards will come toward each other, but they'll never really strike each other because the magnets repel, and then they bounce off in the other direction. So that's a pretty close approximation to an elastic collision. All right, now, so in elastic collisions, when you apply the conservation of kinetic energy, you can derive this formula. And I believe that's derived in your text. And by the way, here, I'm going to be using the primes to indicate velocities after the collision. So this says that the difference of the velocities before the collisions is equal to negative the velocities after the collisions. And it doesn't matter what the masses are on these objects. Okay, so here's an example. We've got a 0.44 kilogram mass moving east with a velocity of 3.8 meters per second. It collides head-on with a 0.22 kilogram ball at rest. The collision is perfectly elastic, no loss in kinetic energy. We want to compute the velocity of each ball after the collision. So we start out with conservation of momentum. Okay, we've seen this before. The only difference is I'm using the primes here now to indicate velocities after the collision. So we start out with the first ball, which has got a mass of 0.44 kilograms, times its velocity. The other ball is at rest, so its momentum is 0. And that's equal to, after the collision, the 0.44 kilogram ball times its velocity, plus the 0.22 kilogram ball times its velocity. Now notice in this equation, we've got two unknowns here, v1 prime, v2 prime. We can't solve that. But we can use this equation, which says that the difference is the velocities, which addresses the difference of velocities before and after collision. So v1 had a velocity of 3.8 meters per second. v2 was 0, and that's equal to minus v1 prime minus v2 prime. Now, if we distribute through the minus signs and we solve for v2 prime, that'll be 3.8 meters per second plus v1 prime. By the way, you could have just as easily solved for v1 prime if you wanted to. Okay, now what we're going to do is we're going to take this and we're going to substitute it in there for v2 prime. So we've got, again, the 0.44 kilograms times the velocity of 3.8 meters per second plus 0 plus 0.44 kilograms times v1 prime plus 0.22 kilograms. But now we're going to substitute in this expression right here. And then we're going to distribute through, and we're going to solve for v1 prime. Notice that we've just got one variable here now, v1 prime. Solve for v1 prime, and that is 1.27 meters per second. And for v2 prime, all we need to do is to go back to this equation right here that said v2 prime is 3.80 plus v1 prime. Now we can solve for v1 prime, v2 prime, and v2 prime is 5.07 meters per second.